Good evening, morning, afternoon, everyone. Good day, whatever. Okay, so today we'll be discussing module 2. Module 2 of the 413, and that's mathematical 2. Mathematical 2. So, remembering what we said in the previous lecture, the whole point of this course is that we analyze algorithms to find out how much time they take and how much space they consume in memory to check which algorithms are better and which are worse. So what this is saying here is that how do we compare algorithms? Do we use their execution time? No, we don't. Do we use their number of statements? No, we don't. So how exactly do we compare algorithms? By using their running time. By using their running time. Okay? So now these are three algorithms to illustrate what he said. And what this is first doing is an assignment algorithm. Array 0 equals to 0 is assigning it a cost of C1, meaning array 1 equals to 0 is C1. Assigning a value to an array is cost C1. So if there are 5 elements in the array, how many times did that program run? 5 times. So if there are 6 elements, how many times? 6 times. That's why it's C1 plus n. Now this is doing the same thing algorithm 1 is doing, but it's using a for loop. Now what I would like you to know about a for loop is that a for loop runs n plus 1 time, and what is inside a for loop runs n times. Let me illustrate. If I say I is equal to 0, I is less than 5, I plus plus. So this would run when I is equal to 0. This will run when I is equal to 1. It would run when I is equal to 2. It will run when I is equal to 3. It will run when I is equal to 4 because 4 is less than 5. And the for loop would evaluate when I is equal to 5. But what is inside the for loop will not run when I is equal to 5 because 5 is not less than 5. But how many times did the for loop run? 1, 2, 3, 4, 5, 6. How many times did what is inside the for loop run? Only 5 times. So a loop or a for loop, a loop generally runs n plus 1 times. What is inside the loop runs n times. So that's how they got this here. Okay, so the C2 executed n plus 1 time. What is inside executed only n time. And if you factorize this, you get this. Okay, so in this third one, remembering what we've said about for loops, this one is a constant, so it's C1. C2 is a loop, this I loop. So how many times will it run? N plus 1. Now everything here is inside this loop. So how many times are they going to run? N times. How many times are they going to run? N times. But this J loop is also a loop. So how many times is that going to run? N plus 1 time. How many times will this run again? N time. So do you understand? I loop is running n plus 1 time. Everything inside that loop is running n time. So this is running n time. This is running n time. But this is also a loop. So it's going to run n plus 1 time. This will run n time again. And that's how they got this and how they got this. Okay? So that's what we said. You compare their rate of growth. Remember what we said about finding the order. That if I have a statement like this, it has the same rate of growth like this. Because as n gets very large, all of this would eventually not matter. So this is of order n raised to power 4. This is of order n raised to power 4. Okay? Now remembering our big O. Big O simply means f of n is less than g of n. So g of n is the upper bound of f of n. In the big omega or lower bound, f of n is greater than g of n. So g of n is the lower bound of f of n. In the big theta, they are equal. So remember these three. Big O, g of n is bigger. Big omega, f of n is bigger. This, they are equal. Okay? So now, we say this is how to find the order of a function. The largest value of n here is n, and that's why it's order n. The largest value of n here is n squared, and that's why it's order n squared. Okay? So visualizing orders of growth. this is also n raised power 4, this is also n raised power 3, this is also n raised power 3. Okay, so now analyzing the algorithms we discussed at the beginning, this algorithm will be of order n, this algorithm will be of order n. So algorithm 1 and algorithm 2, even though this had fewer lines of code, even though this would probably run slower, I believe, than direct assignment, but we don't use that to compare algorithms. What do we use? Their running time. So based on their running time now, what does that mean? That these two are equal. Okay, but algorithm 3 runs O raised by n squared time. And what does that mean? Okay, so what I want you to realize is that O raised to power n square is bigger than O raised to power n. What does that mean? That this runs faster. This will probably take less memory. Okay, so this is a recap of our asymptotic notation, that while n is greater than n naught, while n is greater than n naught, f of n would be smaller than cg of n, or cg of n will be bigger than f of n. So this is the upper bound. Okay, so now let me quickly explain what this slide is saying. It said we should prove that 30n plus 8 is of order n. What you do there, what they are just trying to say, we know that what this will be our f of n. That means there's a g of n that is bigger than f of n. Remembering, there's a g of n that is bigger than f of n, or there's an f of n smaller than g of n. So what does that mean? That means for some certain constants, remembering our definition, c and n naught, such that n is greater than n naught, f of n is less than g of n. So what they are telling you to prove is that 30n plus 8 is less than cn. This is constant cn. How do you prove this? We assume that c is 31. Because the base here is 30, we're just assuming a greater value since we know it's already bigger, and we assume our n naught is 8 because of this constant 8. Okay, so moving on, we said 30n plus 8 is less than g of n, sorry, cn, and we said c is 31, n naught should be 8. That means 30n plus 8 is less than 31n. Bring this to the other side, is less than n. That means n is greater than or equals to 8, which is the same thing here. We said that n has to be greater than or equals to n naught, and from here we see that n is greater than or equals to 8, meaning that of a truth, therefore 30n plus 8 is order n. So when they say prove that something is of a particular order, what they are trying to tell you, get that constant c, get that constant n naught, and from there you can prove it. So let me use another example to explain that. They said prove that n plus 2n square is of order n square. What does that mean? That means it's the same thing. N plus 2n square is less than a particular function cn square, not cn this time because it's of order n square, cn square. So here we can say let c be 3 because here it's 2, so we can say let c be 3, and we can say let n naught be 0 because here is negligible, there's no value. So we can say n plus 2n square is less than 3n square. N is less than n square, which is definitely true. Now we test. We said n naught is 0. We can say when n is 1, 1 will be less than 1 square. We can say when n is 2, 2 will be less than 2 square, as 2 is less than 4. And if you continue increasing values of n, you find out that it's the same thing. What does that mean? That actually n plus 2n square is actually of order n square. So what am I saying now? When they tell you to prove something of a particular order, identify c based on the order of the function. Like here, the ordered function was from here, so our c will probably be the next value after this, that's after 2, so c will be 3. Then identify a base n0. Here it was 0 because this is negligible. This did not really affect the equation. Okay, good. So moving on, this is a recap of big omega. These are examples. This is a recap of big theta. We discussed that in the previous lecture. Okay, so now this is the next thing I want you to learn. This is a key slide in this lecture. You need to understand the magnitudes of orders. From this slide, it said log n is smaller than n. N is smaller than n log n. N log n is smaller than n square. N square is smaller than n cube and n4 and so on and so forth. N raised to power 4 is smaller than 3 raised to power n, or smaller than 3 raised to power n, and so on and so forth. Now some orders were not stated here. Let me state them now. Log n is smaller than log n. N square is smaller than n square log n. N cube is smaller than n cube log n, and so on and so forth. So from here you can see the orders of magnitude. It's important to remember them so that you'll be able to compare functions. Now these are simple logarithm rules. Log x, for instance, log x raised to power y is same thing as y log x. Log xy is same thing as log x plus log y. Log x over y is same thing as log x minus log y. Okay, so it's important you familiarize, especially this one, pretty much everything actually. It's important you learn all these logarithm formulas. Okay, now we'll be very practical with this slide because this is the crux of this course actually. In the first example, is f of n is equal to log n square. Log n square, remembering our former rule, log xy is same thing as y log x. Log n square is the same thing as 2 log n. That's what? Order log n. G of n obviously is of order log n. So f of n and g of n are equal, and that's why it's big theta. Now in the second equation, okay, in the second equation, f of n is of order n, g of n is of order 2 log is of order log n. So this f of n is bigger than g of n, so g of n is going to be the lower bound. For instance, in this one, f of n is of order log n, g of n is of order log n. G of n is bigger than f of n, and that's why it's upper bound. Here f of n is of order n, g of n is of order log n. N is bigger than log n, so g of n is the lower bound. Let me skip to this one. This is a constant. Remember, any constant is of order 1. Log 10 is also a constant because if you type log 10 in your calculator, you get a value. So these are both of order 1 and they are equal. Here f of n is of order 2 raised to power n, and here is of order n square. 2n is bigger than n square, so it's the lower bound. And same thing, 3n is bigger than 2n, so it's the upper bound. So it's very important you know your orders of magnitude. These are theorems, common theorems basically. Transitivity: if A leads to B and B leads to C, it can be inferred that A leads to C. So if f of n is equal to big theta of g of n and g of n is equal to big theta of h of n, that means h of f of n is equal to big theta of h of n. Okay, reflexivity is for the same function, f of n and f of n. So what does that just mean? That f of n is obviously equal to big theta of f of n, f of n is equal to big of f of n, f of n is equal to big omega of f of n. In symmetry, if f of n is equal to big theta of g of n, that means g of n is equal to big theta of f of n. It's only equal in theta. Why? Because in theta, g of n is equal to f of n. So it's like saying if a is equal to b, b is equal to a. That's what symmetry means. Now for transpose symmetry, if f of n is equal to big O g of n, that means g of n is equal to big omega Why? It's like saying if f of n is less than g of n, which is what that means. That means g of n is greater than f of n. That's just what they are saying. So if f of n is equal to big O g of n, that means g of n is equal to big omega g of n. So that's how you apply that. Okay? So these are also, we learned logarithm formulas. These are summation formulas. I advise you just remember the arithmetic series, the geometric series, and this special case. So these three are very important, very important. Now finally we round up with this mathematical tool. What they are just saying is that to prove any mathematical statement is true, for instance, if I say a function s of n is true for all n greater than or equals to 1, that means I have to prove it's true when n equals to 1, and I have to prove for subsequent values of n greater than 1. For instance, if they say prove that 2n plus 1 is less than or equal to 3 raised to the power n for all n is equal to 3, that means I have to prove when n is equal to 3. That would be 2 into 3 plus 1 less than 3 raised to the power 3. That's 6 plus 1, 7 is less than or equal to 8, which is true. But I can't just stop here. I have to check for subsequent values of n. So I'll check when it's 4. That will be 2 into 4 plus 1 less than 3 raised to the power 4. This is 9 is less than 16. It's true. If you like, you can go the third iteration and you still find out it's the same thing. So if it holds for the base case, if it holds for subsequent values of n, that means this equation is true. Okay, so thank you very much. I pray God grants you understanding. That was mathematical tools. Thank you.